Hi, everyone. My name is Dion Rossiter, and I am the Executive Director of Science at Cal. And I am here to welcome you and welcome everyone to our July Midday Science Cafe. It's so exciting to be here and to have you here joining us. If you've been with us before, you know we feature two scientists, one from UC Berkeley and one from Berkeley Lab. So, The Road to Net Zero, featuring Daniel Sanchez and Chet Hopp. So, let's go ahead and get started. We are going to begin, as usual, with a land acknowledgement. We recognize that Berkeley sits on the Huchun territory, the ancestral and unceded land of the Ohlone people, the successors of the historic and sovereign Verona Band of Alameda County. This land was and continues to be of great importance to the Ohlone tribe and other familial descendants of the Verona Band. Every member of the Berkeley community has and continues to benefit from the use and occupation of this land since the institution's founding in 1868. By offering this land acknowledgement, the Berkeley community not only recognizes the history of the land on which we stand, but also recognizes that the Ohlone people are alive and flourishing members of the Berkeley and broader Bay Area communities today. So thank you so much for allowing me to start us off with that land acknowledgement. I just want to remind you all that our summer programming is coming to an end in August. We have one more, August 19th on the periodic table. Of course, we will start back up in the fall, but as for our save the dates, we're running low here. So I just want to make sure you all have that on your calendars. Make sure to stay tuned for more details about what that entails, the periodic table. I will go ahead and just introduce Science at Cal a little bit. Science at Cal, what we do is we bring the wonder and excitement of UC Berkeley STEM research to the community. All of our events and programs are free and geared towards public audiences. We're so happy to have you with us today and every other day. We will be going live with some of our programming in the fall, so stay tuned for that as well. We host programs, cafes, of course, these sorts of lectures. We go to festivals, street fairs, Cal Day, and more. You name it, we'll be in the community, ready to see you live once again, coming soon. We partner with folks across the Bay Area at different organizations on and off campus. Before I hand things over to Jen, I just remind you a few things about this lecture today. It will be recorded, so no worries. If you want to watch something again, or if you want to share this with your friend, you can go ahead and do that. We'll send it out after the program. There's also live transcript that you can click. There's a button at the bottom of your screen if you want to watch live closed captioning as we go. The third thing I want to mention is that oh no, I think that was it. Oh, I want to tell you that there you can ask all of your questions in the chat. There's two options. You can enter them into the chat and you can enter them into the Q&A box. Either way, they will be answered by our presenters. So feel free to do that during each one of their presentations and at the end when we enter our Q&A session. All right, I'm handing things over to you, Jen, now.
Awesome. Thanks so much, Dee. As Dee mentioned, my name's Jen Tang, and I'm the Director for Federal and Community Relations at Lawrence Berkeley National Laboratory. So as folks might know, and you may have heard me say this before, Berkeley Lab is one of 17 US Department of Energy national laboratories across the country, and we are supported by the DOE Office of Science, and we're managed by the University of California. All of the research we conduct at Berkeley Lab is unclassified. And since our founding in 1931 by a UC Berkeley physics professor named Ernest Orlando Lawrence, Berkeley Lab has been dedicated to advancing the scope of human knowledge and seeking science solutions to some of the greatest problems facing humankind. This year actually marks the lab's 90th birthday, and as we celebrate our past achievements and imagine what discoveries the next 90 years might bring us, we hope you'll visit our 90th anniversary webpage, which features a number of opportunities to engage with us, including an upcoming lecture on Friday, July 30th, where we'll be talking about some of the lab's exciting cosmology research. Now, today, Berkeley Lab researchers develop sustainable energy and environmental solutions, create useful new materials, advance the frontiers of computing, and as you'll hear about if you tune in on the 30th of July, probe the mysteries of life, matter, and the universe. Our main campus is nestled in the Berkeley Hills, which is just above the UC Berkeley campus. And we employ about 4,000 people, about 1,700 of whom are scientists, engineers, and faculty members. About 500 of our employees are undergraduate and graduate students. We like to think of these folks as scientists who are just beginning their research journey. Now, the lab's proximity to Cal and our close ties to the UC system create a really unique and synergistic environment for scientific discovery. And a number of the lab's researchers have affiliations with one of the UC campuses, either as a student, postdoc, or professor with a joint appointment at the lab. So as you can imagine, Berkeley Lab's relationship with the UC Berkeley campus is especially close, and our institutions have joined forces to advance science across a number of frontiers. And one of the main motivations for creating Midday Science Cafe is to share with you examples of compelling and complementary research from both of our institutions. And we hope you enjoy today's presentation. So with that, let me kick it back over to Dee, who's going to introduce our first speaker.
Thank you, Jen. It's so wonderful to be partnering with you every month. I'm going to stop share and I'm going to bring Daniel Sanchez up to the screen. Hi, Dan. So as he begins to share his screen, I'll go ahead and introduce him. Daniel Sanchez studies engineered biomass and bioenergy systems that remove CO2 from the atmosphere. Trained as an engineer and energy systems analyst, Sanchez's work and engagement spans the academic, non-governmental, and governmental sectors. As an assistant cooperative extension specialist, he runs the Carbon Removal Lab, which aims to commercialize sustainable carbon dioxide removal technologies and supports outreach to policymakers and technologists. Oh, that's a hard word, technologists in California and across the United States. So as I butcher that last word, Dan, I'm going to hand it over to you so I can stop talking.
Outstanding. Well, thank you so much for the introduction, Dee. My name is Dan Sanchez. I'm a faculty member in the Department of Environmental Science, Policy, and Management here at UC Berkeley. And today I'm going to talk to you about innovative wood products, forest management, fire, and CO2 emissions in the state of California. These are some of my favorite topics, and I'm excited to share some of my work with you. So as Dion mentioned, I have an appointment at UC Berkeley as a cooperative extension specialist. This is a great job because it gives me not only the opportunity to run an academic research lab and do research, which as she mentioned is focused on engineered biomass and bioenergy systems, particularly those that can remove CO2 from the atmosphere, thus reducing future climate change. I also do a lot of work that's categorized as outreach and extension, and that involves working with technology developers and policymakers, primarily in the state of California, to really focus on developing new biomass markets and new wood products markets in the state. So I want to start by setting the context, and this is something that needs relatively little introduction for most residents of the state of California. California is experiencing a wave of extreme and catastrophic wildfire with consequences for the state's carbon emissions, for the functioning of the state's forests and water systems, as well as consequences like loss of life and property that come from catastrophic wildfire. And the state is working very, very hard to change the way it engages with its forest sector, to change the amount of management that we are doing, and to encourage forest restoration across the state of California. Now, this wildfire problem, I think in many ways, is a direct consequence of climate change. Climate change is leading to prolonged periods of droughts, drier weather conditions in the state of California. Very, very strong winds and wind-blown fire events that are new kinds of fire behavior. I really think that, climate change coupled with historical forest management and fire suppression policies kind of gets us to the situation that we have right now. And when I describe this climate change impact with catastrophic wildfire and forest management, I'd like to emphasize kind of two aspects of the climate problem. The first thing that we need to think about as Californians is how can we reduce the current climate change impacts? These are things like the catastrophic wildfires, of which we had 5 million acres. fire last year in the state. This is a question of climate change adaptation. It has to do with how we deal with the climate and weather that is impacting us right now, but to reduce hazard for Californians. The second question we ask about climate change is, how does California reduce future climate change, therefore reducing the amount of hazards and fire impacts we're experiencing into the future? This is known as the mitigation of climate change. And it has to do with how much CO2 on net the state puts into the atmosphere every year from its industrial processes, its electricity sector, and from its land use. Now, I think that the potential solution to this problem, as I've set forth to you around fire and climate in California, has to do with innovative wood products. And that might not be a term that you're particularly familiar with. What I'm really referring to are new and value add uses of the fiber or biomass that comes from trees and that comes from forests within the state of California. So one example of a wood product is electricity. We actually take a large amount of biomass, it's typically waste biomass from California forests, and we make electricity right now. We're actually in the process of scaling up new plants in the state that will not only make electricity, but also capture their CO2 emissions and store them underground. A second option that we have is to make building materials. You know, most houses built in the state of California are made out of wood. I live in a wood house, and I'm coming from you one right now. We build a lot of things out of wood materials, and that not only can displace things like steel or cement that we use to build particularly taller buildings, but also store carbon out of the atmosphere, again, in a long-lived product. Another example of a building material is what's known as mass timber or engineered wood products. These are very, very large structural wood products that we can use to build buildings that are up to 18 stories high. So these are really kind of new innovations, new buildings, and we want to build a lot more wood in our urban cores by building tall buildings out of wood. One last example of an innovative wood product is transportation fuels. So rather than drilling for petroleum and refining it into gasoline and diesel, which we use to run our cars and trucks around the state, we can actually turn woody biomass and trees into transportation fuels. And this is a particularly promising opportunity, and I'm happy to talk about it a little bit more in the Q&A. So the main problem that we're dealing with here is that if the state wants to scale up its pace and scale of forest restoration, it can really do one of two things. One thing it can do is to introduce more fire back onto the landscape. This reduces fuel loads and reduces the intensity of future potentially catastrophic wildfires. This is a technique known as prescribed fire, and we're working hard to scale that up within the state of California. It's generally not done on the scale that we envision doing it in the future, and there are a lot of regulatory and economic barriers to scaling it up. So another option to promote forest restoration is to do what's called forest thinning or mechanical vegetation removal. This is where some trees are selectively harvested from the forest stand in order to promote stand resilience and reduce fire risk. Some of those large trees are taken to sawmills where they make wood products, things like dimensional lumber for houses or furniture or paper. But actually a large amount of that forest biomass is essentially left in the forest. The tops of the trees, the branches of the trees, the small diameter trees that are too small to bring outside of the forest are typically piled and either burned in place or left to decay within the forest. Now, this is essentially forest biomass that goes to waste. And we think there's a real opportunity to take that biomass and make innovative wood products, conferring a lot more economic and environmental benefits for the state than just simply leaving the biomass there in the forest. And so the question I'm really interested in answering is, can these innovative wood products, some of which I've already described to you, help California align its climate change mitigation goals, meaning reducing its net CO2 emissions, as well as its climate change's adaptation goals, including things like reducing the amount of catastrophic wildfire we have in the state? So when I try to answer that question, I ask things like, what are new wood products that can attract higher prices? And are any of those particularly ready to scale or particularly effective when considering California and California consumers and California policy? The second question you can ask is, say we have these new wood products and these new markets are built, what does that mean for forest management and for fire risk reduction across the state of California? And then finally, we really want to understand the overall carbon impacts of expanded management, which does reduce the amount of carbon standing in a forest, but also new markets with the innovative wood products as integrated. And I'm going to walk through some of those questions a bit later in the presentation. I want to say there are some reasons why I'm pretty excited about this. One is that I think there are innovative wood products that are sufficiently commercially ready and ready to be deployed in the state. As I mentioned before, this can look like mass timber, these large buildings built out of wood and engineered wood products and panels. The second one has to do with liquid and gaseous transportation fuels. These can be things like gasoline or diesel, or even renewable natural gas or hydrogen derived from forest biomass. Another reason why I'm so excited about innovative wood products in the state of California is because we think they have an important role to play in the state's goal of carbon neutrality. So currently the state has an executive order to reduce its net economy-wide CO2 emissions to 0. That means absolutely no net CO2 emissions from the state by the year 2045. But as I show here in the yellow line, the state's current plans actually don't get us all the way to 0. So there needs to be additional measures and additional actions, the introduction of so-called carbon dioxide removal technologies to help the state meet its 2045 carbon neutrality goals. I've worked with some colleagues to think about how we can manage and change our lands differently, how we can convert that waste biomass I was talking about before to fuels and capture and store the CO2 associated with them, as well as introduce other carbon removal technologies like direct air capture to actually pull 125 million tons of CO2 out of the air per year in the state by mid-century and really help the state meet its carbon neutrality goals. Now, the last reason I'm so excited about this is because the state and federal governments have actually really gotten their act together and agreed to scale up to that 1 million acres per year forest restoration goal. This was done in a pretty mundane document, a memorandum of understanding between the state of California and the Regional Forest Service. But most importantly, the parties committed to treating 1 million acres per year for fire risk reduction. And I think we're doing a lot in the state of California to help realize and meet that vision, including encouraging new innovative wood products industries. I want to conclude by showing you some of my work around innovative wood products and carbon dioxide. This is some work that I've done recently for the state of California. It's in the process of being published. We found that if the state did meet its forest restoration goals, then we could reduce wildfire hazard over the next 40 years on about 12 million acres of California's land. Now, we only have about 30 million acres of forest land in the state of California. So this is a really large reduction and a really large hazard reduction. At the same time, we actually can reduce and avoid 3 million, so about 10% of California forests, avoiding these kind of potential stand replacing or these very catastrophic wildfires, the ones that spread to hundreds of thousands of acres and severely threaten life and property in the state. We also find that actually the area where this makes the most sense to implement is in the Sierra Nevada region of California. This is where we're experiencing not only a relatively large fire risk, but we have a fairly depressed wood products industry. And we find that doing forest restoration and scaling up innovative wood products works particularly well on Forest Service land within the Sierra Nevadas. This is like the Sierra National Forest, the Plumas National Forest, Lassen National Forest. Finally, we find that this is a good thing for net CO2 emissions reductions. We get about 6 million tons of better CO2 outcomes per year relative to a business as usual scenario. And we do that by tracking both the carbon in the forest, the carbon that can be burned under different wildfire conditions, as well as the carbon stored in wood products and the displacement of fossil fuels over this 40-year period we're modeling. And I want to draw your attention just to the dark black line on the far right-hand side of the figure. These are the net carbon outcomes when we implement forest restoration and do more thinning. And this, it just shows that we get the best net carbon outcomes associated with this whole, with this scenario. So we find that we do have this opportunity with innovative wood use to support, widespread fire hazard mitigation in the state, as well as reduce net CO2 emissions. And, this is one way that we can really align kind of our need for both climate change adaptation and climate change mitigation within the state of California using our forests. I'm going to stop there and happy to take any immediate questions from the audience or from Dion.
Excellent. Thank you so much, Dan. That was great. So here's a question. Wouldn't the demand for more wood drive demand for more trees that we cut down in a non-sustainable way? How do we ensure that the wood products are made from waste or thinning trees, as opposed to essentially creating a bigger problem?
Sure. This is a really great question. The first thing I'll do is kind of defend the sustainability of California's forest practice rules, the way that we regulate timber harvest and fuel reduction on private lands in the state. I think that, when it has to do with the kinds of the limitations on the prescriptions we're doing, as well as the protections for water and other and soil and other kinds of sustainability, that California probably has the most stringent forest practice regulations, certainly in the United States, if not in the whole world. So I think we can be fairly confident that the biomass that we are producing in California at least complies with all of California's laws, and in many senses is probably some of the most sustainable biomass that we do have. That being said, we don't want to be diverting large trees that we can be used to make long-lived products into something like biomass power, where there's less of a carbon benefit that comes from that, nor do we want to just leave these trees in the forest. And so we're particularly focused on the economics of this waste biomass and trying to understand if the delivered prices at these new innovative wood products facilities could justify mobilizing these residues. It involves chipping and transporting the wood out of the forest. We also find that because this material has very, very little value right now, that this is going to be the kind of wood that goes to these energy and transportation fuel applications. They're typically going to be using the low value wood that's left in California's forests. So I think there are a lot of aspects to that, but hopefully those are 2 points that help.
Awesome. And speaking of transportation fuels, how do you make transportation fuels out of trees?
Sure. And I just saw one question. We are considering the energy and emissions of the harvest, processing, and transport in this analysis. The way that we make transportation fuels out of biomass, it's actually very convenient because biomass contains the same elements that are in gasoline or diesel or methane or the things that we use to run our vehicles in the state. And that's carbon, hydrogen, and oxygen. They're just different arrangements of those carbon, hydrogen, and oxygen atoms. So we use chemistry in order to rearrange the carbons and the hydrogens and the oxygens that are in forest biomass into the kinds of fuels that we can burn in our engines and use in our industrial processes. That often proceeds by essentially heating the biomass in a very low oxygen environment at a high temperature. It's a process known as gasification, and it turns the biomass from its solid form into a gas. We then clean up that gas and then use downstream catalysts and other chemical reactions to make the fuels that we want as an end product that comes from the forest biomass.
Awesome. Thank you. Before we hand things over to Jen and Chet, do you want to say anything more about including the cost of harvest, processing, or transport?
Sure. I think that's an important thing to consider in a life cycle assessment. If we really want to understand what happens in the forest, what happens out of the forest, what happens in between the forest, and whether it's the best net carbon outcome for the state of California, you need to consider the whole supply chain. And so that's a really important part of doing this analysis right.
Right. Definitely not something we can ignore from the get-go. Okay, excellent. Let's hand things over to Jen and Chet. So come on up, Jen.
Our next speaker is Chet Hopp. He's a postdoctoral scholar in the Energy Geoscience Division at Berkeley Lab. And his research interests include the relationship between seismicity and subsurface energy applications, which include things like conventional geothermal reservoirs, enhanced geothermal systems, and carbon dioxide storage, which he'll share more with you about in just a minute. His other research interests include the seismic monitoring of volcanoes, which sounds cool, waveform-based event detection algorithms, and open source software development. In his spare time, Chet is an avid skier, so we might see him out on the slopes this winter. Chet, over to you.
Hi, everybody. My name is Chet Hopp. I'm a postdoc and a seismologist at Berkeley Lab in the Energy Geosciences Division. I'm going to talk about geologic carbon dioxide sequestration and its relation to seismicity and faults. I tried to give this talk earlier today to some of you live. Apologies, I was kicked out about halfway through, but hopefully you find this recorded version interesting. And if you have any questions, please feel free to reach out. So geologic CO2 sequestration, or carbon sequestration, I'll probably end up calling it throughout the talk, is a fancy way of saying taking carbon dioxide from a source, any source, and injecting it below the ground, where in theory it will stay and stop contributing to global climate change. So a number of entities around the world have run climate models, basically looking at how we can stay below 2 degrees C or 1.5 degrees C of global warming. And in all of their climate modeling, they come to two conclusions. One, obviously, we need to be rapidly eliminating the emissions that we're currently producing. But on top of that, we're going to need to take CO2 directly out of the atmosphere and store it somewhere. So CO2 sequestration is obviously relevant for mitigating the emissions that we produce currently. For example, from natural gas power plants, as we transition to renewable energy, we're able to capture the carbon dioxide coming out of the stacks and inject it below ground. And then there are a number of industries, the cement processing industry, for instance, that are very difficult to decarbonize. And so while we look for alternatives to those, we can attempt to mitigate their emissions by capturing and storing below ground. Then in terms of negative emissions, we can actually take CO2 directly out of the air and store it below ground. That's what's shown in this kind of rendering of a direct air capture plant here on top. And Dan touched on bioenergy, biomass energy, where we take renewable sources of energy, like trees, basically, wood byproducts, and burn them for fuel or for an industrial purpose, and then capture that CO2 and inject it into the ground. So we've been doing this to the tune of millions of tons of injected carbon dioxide at a number of locations worldwide, shown in red. And there are a number more planned, shown in blue. But millions of tons per year of injection is not nearly what we need to meet our climate goals. We need to be a couple of orders of magnitude larger than that, into the billions of tons of injected CO2 per year. And so that's going to bump us up against a couple of pretty substantial obstacles, not the least of which is the threat of induced earthquakes. So we know that we induce earthquakes through a number of industrial processes, either taking stuff out of the ground or putting stuff into the ground. Obviously, CO2 sequestration is putting something into the ground where you will increase the pressure and increase, therefore, the likelihood of inducing an earthquake or triggering an earthquake. And we know this to be an issue already over the last decade or two in the central US, shown in this map, where previously there was a predictable tectonic rate of earthquakes starting in 2008 as a result of the fracking revolution and wastewater injection of the fracking wastewater. There was an enormous uptick in the number of earthquakes. And so the volumes that were injected and are still being injected in some parts of the United States related to the oil and gas industry are somewhat similar to the volumes of carbon dioxide that we're going to need to inject to meet the climate goals. So it's a question that needs answering. And a somewhat related question to how do we avoid large earthquakes is, how do we avoid the carbon dioxide that we put underground leaking back out and making all of our work moot? The basic idea of sequestration is you put the carbon dioxide into a reservoir at depth, and the reservoir could be a number of things. It could be an old oil and gas reservoir. And there's a cap rock, what's called a cap rock on top, which is a layer of basically clay most of the time, which prevents fluids from buoyantly moving upwards. And those cap rocks are almost always chock full of fractures, but those fractures are usually not permeable unless we inject CO2 and increase the pressure and induce movement on these fractures, which can bring about leakage, which is either seismic or aseismic, meaning that it doesn't generate any felt earthquakes at the surface, but could still be leaking CO2. So kind of how these faults and caprocks work, what the effect of injection is on them, is not a well understood question. So that's what we're trying to answer with one of these experiments that we're doing at the lab. And when I say at the lab, I mean in northern Switzerland at a underground rock laboratory, Monterey, where they're actually doing a lot of research into the disposal of nuclear waste, but it happens to be a perfect caprock analog because there's a fault zone that runs through it, through a clay layer. And so we've turned up and drilled a number of boreholes from the tunnels into the fault zone and near the fault zone, and then instrumented it. So the idea here with this experiment is that we're going to inject water into the fault zone, create an artificial leakage, and then observe what happens to the fault in response. So is there seismicity? How much does the fault move? How much does it move without seismicity? And kind of where does the water go? So the fault here in this cartoon has a top and a bottom with a kind of a squishy middle portion, which we know because it's been pretty well characterized over the last number of decades. And we're injecting into this borehole V2. Water goes in at the red X here at the top of the fault into this instrument here, which is designed and manufactured by Geoscience's measurement facility at Berkeley Lab. And it doubles as a displacement probe. So water goes into the center, and then we measure how the top of the fault moves with respect to the bottom of the fault. It's a really clever device. And it enables us to directly measure fault slip, which was not really possible before. And so we've installed a number of other instrumentation systems. Two of them, seismic acquisition system, which is basically monitoring for earthquakes, monitoring ground movement, which are installed at basically where the X's are in these 5 wells here. And we've also installed fiber optics. So these are the sort of cable that delivers your internet, for example. But we're using the cable itself as a sensor here. So at each point along the sensor, we know how the cable is stretching or contracting. So it's a way for us to know how the entire rock volume is stressing and straining during the experiment. So the experiment looks like this. It took place over 10 hours. We injected about 500 liters of water in total, which doesn't sound like a lot. These are flow rates in blue, liters per minute with time, and at pressures of numbers of megapascal. But really what that just means is that we're able to open the fault, allow fluid to disperse into the top of the fault, and then when we stop injecting, the fault comes closed to some degree. So there are 6 injection cycles, and I'll tell the story of the experiment through 3 of them, the first, the third, and the 6th, which were when somewhat notable things happened. So here we are in our undisturbed state. We start injecting and the fluid migrates out in theory, all directions. We don't really know at this point. But we do know from the displacement probe, which doubles as the injection probe, how the top of the fault moved. So it started here in the purple, over on the left figure, migrated up and to the right until we stopped injecting, at which point it came back about halfway to where it started. So we induced a permanent shear of the fault up and to the right. And we also induced an earthquake, which was located about here, probably just a little bit outside of the patch where the fluid was. I should mention that these earthquakes are not felt by anybody in the tunnel. We're 40 meters away from where this occurred, and they're very tiny. We don't know the exact magnitude, but they're negative magnitudes, which is actually possible. It's a logarithmic scale of earthquake magnitude. So basically the patch of fault that ruptured is somewhere between the size of your hand and the size of your desk, so pretty tiny. Okay, cycle 3 is when a lot of interesting things happen. So we know that the top of the fault moved up into the right, so we can postulate that the fluid also moved in that direction. But we didn't know that for certain until cycle 3, when fluid actually started rising in borehole B1, where there was no fluid previously. So we established a hydraulic connection and proved that we had established our leak that we were looking for. Fluid started rising and unfortunately fried some electronics that we had in this borehole. But we were able to actually measure the the rupture of the fault through borehole B1, which actually canted the borehole a little bit. So what's being shown in these curves is how much the cable is stretching. The fiber optic cable is stretching with depth in the borehole. We're injecting fluid at 40 meters down here. And so as expected, we see a signal there. That's not groundbreaking. But over here on the right side, where we're not doing anything in this borehole B1, we see a strong signal at the depth of the top of the fault. So this is proving that there's something going on. The fault is rupturing through the point of intersection between borehole B1 and the fault. So that's the size of our leak, 15 meters minimum at this point. And we also have earthquake data. So we have, these are the cumulative number of earthquakes throughout the experiment. And most of the earthquakes occurred during this cycle 3. So something large happened. Either the fault was slipping more rapidly, a much larger portion of the fault was slipping. We don't know exactly why, but this is when the greatest number of earthquakes occurred and when the fault ruptured through to B1. And this is cycle 6. So at the end of all of the injection cycles, when we think the fault patch that we've established, the kind of leak, is about the size of this blue area. Fluid started rising out of the top of B1, which is actually why we had to stop injecting. But not before we generated one more earthquake, a little bit smaller than the first one. And it was located out here past B1. So again, everything is consistent with this up and to the right rupture, fluid migration, and seismicity. So what did we learn? Well, it was actually an immensely successful experiment. We created a leak. We monitored it very well, and all of the data streams indicate the same thing, this sort of trend of movement, seismicity, fluid migration from the injection borehole to that borehole B1. And so we've proved out the concept of monitoring a cap rock like this with all of these different systems, including the fiber optics, which is very important. And interesting from a seismology perspective is the fact that for the size of that leak, the amount of seismicity is probably pretty small. So a lot of the leak is occurring without seismicity, which is an important point. So what does this mean for carbon dioxide sequestration in general? Well, again, all of these methods of monitoring are very effective and should probably be used for monitoring carbon dioxide sequestration projects at a field scale, large scale. They're somewhat expensive, especially the cost of drilling boreholes to those depths. But relative to the cost of, well, climate change, but even just to the cost of a project like that in general, the costs of these monitoring systems are fairly small. So you get more information and you're better able to de-risk your project. And the fact that there were few earthquakes is actually quite important. So usually these projects can be monitored from the surface by tracking how seismicity migrates with time. So that's kind of like how your fault is rupturing. You can watch it with little earthquakes. But if you have a leakage and it's aseismic, meaning that there is relatively little seismicity, it's very important that we be measuring displacement of the fault directly or indirectly with fibers in order to sort of pinpoint where those leaks might be occurring. So we have another experiment coming pretty soon, actually. We'll more or less repeat the one we did to see how repeatable it is. And then further down the line, we're going to add the chemistry component to it by, instead of injecting water, injecting carbon dioxide brine or carbon dioxide gas, and see how that changes things. So that's the end of my talk. Thank you very much for listening. And I apologize that I wasn't able to give this live, but again, if you do have any questions, feel free to reach out to me. I'd be more than happy to talk. And thank you again.
All right, folks, unfortunately, we have lost Chet again. So Dan, I am sorry. We're going to bring you back up to the screen if you don't mind answering a few more questions.
I don't. The good news is that there's a lot of questions in the Q&A.
Yes.
Yeah. So Jen, I said that there's so many questions in the Q&A that he can go in and push answer live, and we can pick the ones that he would like to answer. So
Perfect.
First, there's proven technology for biomass within CCS. If so, I sure haven't heard of it. Please enlighten me.
Sure, no problem.
CCS, start there.
Yes, so CCS is a technology known as carbon capture and storage. We can apply it to a wide range of industrial facilities. These are things like power plants that run on natural gas or run on coal or run on biomass. We can apply them to oil refineries. We can apply them to steel and cement making. And importantly, we can apply it to biorefineries, which are facilities that take biomass and turn them into other valuable products. So there are really two things I want to highlight in the biomass with carbon capture and storage place that are pretty exciting. One is that this is a technology that has been commercially deployed and is actually rapidly scaling up in the Midwest of the United States. Now, what we do in the Midwest is we harvest corn, which is not the most sustainable feedstock, but it is the basis of our existing ethanol transportation fuels in the country. And we ferment that corn along with yeast to make transportation fuels. In this case, we're making ethanol. That ethanol is 10% by volume of what you burn in your engine, very likely, in the state of California. So these facilities vent pure CO2 into the atmosphere off the top of their fermenters. And there have been already several, I would estimate about a half dozen facilities that are implementing carbon capture and some form of CO2 storage or some form of CO2 utilization associated with that CO2. And we actually just saw the announcement of 3 multi-billion-dollar pipeline projects that want to tie up all the ethanol biorefineries in Iowa and Nebraska and Minnesota, where unfortunately we don't have the geology to put the CO2 underground. There have been 3 separate project proposals in the past few weeks to essentially build very, very large CO2 transport pipelines to move that CO2 to Illinois or to North Dakota or all the way to Western Nebraska, where we think we can store the CO2 underground. So I think in the ethanol industry, CCS is really starting to grow. Now that's different than, say woody biomass to fuels or biomass to electricity, which again, we use woody biomass for in the state of California. But I would point you to a project that's been announced in the state of California in a city known as Mendota. It's west of Fresno in Fresno County. And there's a partnership between a technology developer known as Clean Energy Systems, as well as several large corporate entities like Microsoft, Chevron, and Schlumberger, to actually build a biomass power plant. They're going to retrofit an old and idled biomass power plant that's already sitting there to make electricity, but also capture all of its CO2 and store it underground. And that's a plant that was announced earlier this year, and one that we're watching really closely in the state because it'll be, the first really successful implementation of biomass power with carbon capture. It'll also be one of the first implementations of actually sticking CO2 underground in the state of California for the purpose of geologic sequestration.
Awesome.
Thank you, Steve. Yeah.
Great. So Chet back? Nope, not yet. What about soil depletion over time within forests where biomass is continuously removed? Is that a concern?
It is a concern, and it's a hard thing to monitor. We know that there needs to be some amount of biomass left in the forest, particularly the greens, the needles on our needle leaf trees. Those contain high amounts of nitrogen that are really necessary for proper soils. I would say that, Steve, it is hard to generalize about the impact of harvest on soil organic carbon in forests. It definitely is an issue that needs to be tracked about and thought about and measured a lot more diligently if we're going to ensure that this is a really sustainable and carbon beneficial industry.
Awesome. Okay. Why don't we go through some of these questions that we've gotten from the audience? So I think an audience member is curious, did you compare from a carbon footprint standpoint, using wood products and refined fossil fuels for the vehicle industry? If so, do you have any numbers you could sort of share with us about that comparison?
Sure, absolutely. And this is one thing that we did consider. Let me bring back up my slides. This is on the net CO2 emissions outcomes for the forest management scenarios that we considered. I moved through this very quickly in the interest of time. One thing I can point you to, though, is the bottom half of that figure. We're essentially showing for the ton of carbon that's in the wood that goes into the process, how much of a carbon benefit we get out of that. And we look at a number of different wood products, both including wood, building products like oriented strand board or glue lam. These are things that we can do where we essentially push small value wood and smush it together to make a strong wood product, or things that are transportation fuels. This can be hydrogen production, including or not including carbon capture or storage. This can be power production that we use to charge electric vehicles, again, with or without carbon capture and storage. Or it can be liquid fuels like ethanol, which is about 10% of what we burn in our cars right now, or things like gasoline or diesel, which are really kind of drop-in fuels that can replace what we burn in our vehicles right now, molecule for molecule. And so we're tracking the amount of process emissions that comes out from the facility, say, for example, due to extra fossil fuel emissions that are necessary to do the conversion, that actually counts against your carbon benefit. But then we're also accounting for the displacement of a fossil intensive alternative. Say, for example, if you're making gasoline or diesel, you are displacing fossil gasoline or diesel. We're also accounting for the carbon stored in products, again, over this 40-year period. So if we say we build a building out of oriented strand board or out of glue lam, it's quite likely that building will still be standing, or at least on a statistical level, a lot of that wood that goes in the buildings will still be standing after 40 years. So we do count that carbon storage benefit. Those are the three kind of gray boxes in the middle of the figure legend, showing the substitution, process emissions, and storage benefits that come from using these fuels. And happy to share more about the life cycle analysis, but a one-for-one carbon payback would be 1.0 right here. A ton carbon goes in and a ton carbon comes out. That's like a good, that's a good like net carbon outcome for the system. Many of these don't get all the way there, but many of them are above essentially this 0.5 ratio. So the carbon benefits per carbon of biomass that goes in is around 50 to 75% of the carbon that you fed into the process in the first place.
Got it. Thanks, Dan. Here's another question for you. Dan, what are the challenges to creating policy, I guess maybe state or federal, that supports developing the technology and the markets for innovative wood products that actually helps the state meet its layers of goals? Fire prevention, job creation, carbon capture, et cetera. What would need to happen next to support this development?
Yeah, this is a really hard question to answer, in part because we just have such a dramatic need to introduce treatments on the ground right now. And many of these things are technologies that are nearly commercial, but not like ready to be deployed, build a plant tomorrow, right, in the state and have it ready to run a week later. We're not quite there, and it does take time and finance and engineering in order to get these projects over the finish line. Another big issue here is that we actually have a really mixed ownership of lands in the state of California in terms of our forest lands. But 1/3 is owned by industrial timber owners, another 1/3 is owned by small private landholders, and then 1/3 is owned by and operated by the U.S. Forest Service. And getting all of those entities to collaborate together, to integrate their wood product supply chains, to share information, to implement similar practices is really hard. I think most of the lagging has been the U.S. Forest Service in recent years, but I think the Forest Service is going to really be stepping up and thinking about this hypothesis and these opportunities moving forward, especially with a goal of them treating 500,000 acres a year by 2025.
Well, like I said, Dan, you have so many questions coming in, and if we go, we still have plenty of time to get Chet up. So we're probably going to do your complete Q&A right now, and then hand things over completely to Chet. Now, I will say this is the first time in a year and a half Midday Science Cafe has ever had technical difficulties. So I feel like we had to hit that wall at some point. So did you see any other questions in that chat?
I did. I really appreciated the third one. This is from Gary. He said, would new wood products as an industry in California allow us to reforest California faster to offset the impact from fires? And the answer to that question is very likely yes. I think if, the reasoning as I see it is if there is more demand for the products that come from forests, there will be more of an economic incentive to plant trees again and to grow the amount of forests that we have in California. So, if we are able to reintroduce commercial wood species into areas where we are reforesting after fire, that does improve the management situation and very likely makes us able to manage the stand much better. We can also think about areas that haven't necessarily been impacted by fires or aren't necessarily the kind of iconic kind of conifer tree systems that we think about when we think about this opportunity. One example in the state of California is we have a broad range of oak and oak woodlands throughout the state. We have beautiful oak trees all throughout California, and there is no commercial market for those wood, for that wood in California, aside from essentially a little bit of firewood that you can buy hardwood firewood throughout the state. I would postulate that if we're able to make things out of wood, say, for example, oak barrels out of those California oaks, rather than relying on French or Eastern US oaks, I think we'd have a lot more incentive to plant oaks, to restore our woodlands, and to generally do reforestation in the state. So I am, yes, the same reason we can pull more waste biomass out of the forest is the same reason we could hopefully reforest and plant more trees.
Excellent, thank you. Well, we answered that one. Is there a way to apply this to the whole world? Do you think other countries, you know, are willing to kind of do the similar things that California is trying?
Yeah, I think California is really trying to be one of the first in the world that's doing this. You know, bioenergy is not a particularly large industry in most of the world, and where it is, it's pretty outdated technology, and it's kind of just break-even economics at best. Where we have advanced bioenergy deployment is really in Northern Europe. And I think a lot of Northern European partners have started thinking about these opportunities to deploy bioenergy with carbon capture and storage. There again, they have kind of, you know, existing governed forests. They have a long tradition of using working forests. They also have advanced conversion technologies, things like biomass gasification that have already been implemented in Europe. So I do think Northern Europe is one of these other places where we really might see this. I would expect this technology, given its cost, its complexity, its cost and its complexity. I think this is something we're primarily going to see in the so-called developed world or OECD countries, rather than being deployed in the developing world. There are a lot of things we can do with biomass and to improve biomass utilization and supply chains in the developing world, as well as to improve forest management in the developing world. But I don't think these kind of large, centralized, very engineering intensive facilities are going to be deployed there first. I think we're really going to start with it in OECD countries.
There are some questions in the chat as well. So one of them being, can you address the monoculture tree farms versus natural forest communities?
Sure. So this is less of a concern in the state of California, where we either have old growth forest that really hasn't been touched, or so-called second or third growth forest that has already been harvested. What we do in California is we essentially harvest the softwood trees that are kind of natural and endemic to the area. And we do these primarily in these forests that have already been disturbed. So you're not talking about harvesting old growth forest. You're talking about kind of the continued management of stands that have already been altered, primarily by both by timber harvesting and by fire exclusion, including the policy we had in California to essentially put out every single fire that started immediately. So it's a little bit different here in California, and I'd be fairly confident that we're really not talking about any kind of monoculture tree plantations. That's different in other forest ecosystems where there's a real difference in species between the natural forest constituents and the commercial plantation type species. And so it's absolutely an important issue to think about when we're considering restoring forests versus managing forests and what that means for climate change really throughout the world.
Yeah, and there was one question. I know we had talked about what the analysis included and what it didn't include. There was a question specifically about whether or not it included emission savings from reducing wildfires. Was that taken into consideration?
That's right. Let me bring up that slide one more time because I think we have a second to do it.
Mm-hmm.
So if I share my screen and go back
Mm-hmm.
to this slide.
Mm-hmm.
We are considering a couple of different things. This is in the top half of the figure. In green, we're considering the amount of carbon that is in the forest. And so we see that actually when we have a very low level of management, that the amount of carbon increases starting on the left-hand side. That increases over time. At the same time, though, we do see a lot of both combustion and post-fire decay of the trees due to the amount of wildfire we're seeing in the system. And that's shown in the red and the pink line there. We're producing almost a very, very small amount of wood products there. So the kind of the yellow and gold colors at the top are really small parts of the overall carbon impact in this, again, this low business as usual scenario. I would contrast that all the way to the innovative wood product scenario where we're doing a lot more management, but also making a lot more wood products. There we see that we're actually reducing the amount of net in-forest carbon that we have in California's forests. And that's probably essential to reduce wildfire risk. At the same time, we see that wildfire risk is absolutely reduced compared to the business as usual scenarios. And when you and the extra benefits of using wood or low value biomass residues for innovative wood products kind of drives the best carbon outcomes. So we tried to draw kind of as much as broad of a system boundary around this whole system as we could.
Yeah, I think what we'll head into next is because you did answer so many of those questions, was there one or two that you want to say, like, I think this is a really great question that maybe everyone should hear the answer to?
Yeah, no problem. Let me go back to that.
That way we don't have to, you can decide what, this is totally not normal how we normally run things, but since you answered them, I felt like, well, there could be things in there that others might find interesting in your responses.
Yeah, well, so, I'll be a little heretical. Steve Bloom asked a question. He said, we're getting rid of internal combustion engine vehicles as fast as we can in California. What market will that leave for fuel producing plants? So what Steve is referring to is the dramatic plans that the state has to deploy electric vehicles. Because these vehicles operate on electricity, we don't need to burn liquid or gaseous transportation fuels within these vehicles in order to propel them. We just charge up batteries and we charge up those batteries using electricity. So I am very supportive of the state's goals around electrification, but I worry that they may not be met. The governor has had a 5 million zero emission vehicle mandate, and we're really trying to scale up and offer incentives for electric vehicle charging, for electric vehicle purchasing, for all the things you need to kind of make electric vehicles catch on in the state. But it hasn't really met the expectations we have to this point. So I think I would hope that we electrify our light duty vehicles, our passenger transportation vehicles as much as we can. I still think that means that we're going to have a residual fuel market that is actually quite large in the state of California for the next several decades. And that includes kind of medium and heavy duty transport. These are things that are harder to electrify, though not impossible. This includes things like aviation, making aviation fuels from biomass. Again, you can get this energy dense transportation fuel unlike the kind of energy densities you get out of batteries, which limits why you can't really fly planes on batteries. So I suspect that kind of the residual gasoline and diesel combustion engines that are going to remain in California's fleet, as well as like the need for transportation fuels, is going to be enough to satisfy. It's going to be enough to create a market for this biomass, and so I'm not incredibly worried about it. I would also note that you can, just like Clean Energy Systems is trying to do in Mendota, California, you can make electricity, capture all the CO2 emissions and put them underground from biomass and still charge an electric vehicle. So, I hope this is complementary rather than really kind of putting fuels versus electricity against each other. I think it's about making cleaner options for transport and industrial decarbonization.
Yeah, we've had a few past Midday Science Cafes where we have addressed these biomass, biofuel, plant source fuels solutions. So that's great. You're sort of adding to this collection of information that we have been sharing throughout the last year and a half. Is there another question you'd like to share with everyone? If not, I'm going to invite Jen back up to give everyone a sense for what our plan is going forward today.
I think we're good.
You're
think the other
good,
ones
yeah.
were relatively small.
Okay.
I'll say one more thing. Laura Lynn Powell asked a question not about the challenges to state policy and making this happen, but what are some of the opportunities that we have? I do think there's a real opportunity actually to use the state of California's very ambitious climate change mitigation policy. You know, the commitments we already have to make low carbon fuels or deploy electric vehicles or reduce our production or consumption of steel and concrete. Like those are the same policies that are going to allow us to use more wood to make products. And hopefully the state can really align the incentives to make this work. And that's the hope that I bring to all of this.
Yeah, and I think we've heard that from other scientists before, haven't we, Jen? That California has such a unique landscape and unique problems that are really relevant to California, but also other countries as a whole. So it is interesting. It's great that we're leading the way in all of these new technologies. So thank you, Daniel, for being here. Jen, take it away.
Thanks both. And, I will say, as Dee mentioned, we have done a year and some change of these events. This is the first time we've had significant technical difficulties. So we appreciate you folks hanging in there with us. Here's the plan, because we think Chet's presentation is really compelling and really important. We're going to ask him to record his presentation at a later time. We will then merge it to Dan's presentation and send out the recording so that you have both presentations. If you have any questions for Chet on his research, we'll make sure there's a way you can share with us those questions. We'll get those answered and make sure that there is sort of a whole presentation. So with that being said, well, I think we'll maybe wrap up.
Yeah. An interesting hour, but we made it work.
Exactly. Chet, thanks so much for your valiant efforts trying to keep logging in. Dan, thank you so much for answering all of the great questions that came in for our audience. I just want to say that, as we close, thanks again to Chet and Dan. Thanks again to all of the great questions we got from the audience. If you want to stay up to date on research coming out of either of our institutions, you can find Science at Cal at scienceatcal.berkeley.edu and Berkeley Lab at www.lbl.gov. With that, folks.
Oh, Jen, you went on mute.
I thought I'd just add to our technical difficulties. With that being said, we hope to see you next month, where we're going to have two presenters talking about some exciting developments on the periodic table, cutting edge research related to the periodic table. So
thank you, everyone. Thanks, everyone. Bye. Have a good evening.